Since I didn't finish everything that I planned to do yesterday, and I just realized I don't have any notes, but I'll just wing it. So, actually, I didn't have it winging it the whole time. And I guess it comes with recently writing a book about it. I do want to mention one quick thing. Coming up towards the end of the month, the last week of February, so February 25th and 27th, class will not meet because I and one of you will be at a conference. So what I'll be doing, instead of getting a substitute in here, because things just go wrong when that happens, I will record something in advance. So I'll be in here some evening, just at the board in front of nobody, and I'll go ahead and post that. So whatever it is I plan to cover that day. So
both the 25th and the 27th?
Yes. Okay. So in a way, you'll still have class. You just won't have to come here to get it. Okay. Now.
I'm teaching my trade class that day, and then I don't have to come in at all. I'll fix that.
Okay. So where I left off last time, Cholesky factorization. Okay. So A is n by n symmetric positive definite, and it's factored into G transpose, where G is lower triangular, and I had written G transpose as a sum of outer products. And I'm going to use that to show you how, so this will be an interesting, well, okay, interesting to me, hopefully to you too, exercise in algorithm development, how to not just get an algorithm that is correct, but also is as efficient as possible. And just for completeness of my notation, the G's here are just the columns of G. And very crucial point, because G is lower triangular, each of these columns, as I go from left to right, has fewer non-zero entries. So G1 can be entirely non-zero, but G2 has to have a 0 at the top, then keeps going from there. So G3 would have the first 2 entries must be 0. And it keeps on decreasing all the way to the last column of G, which is entirely 0, except for 1 entry. Okay, so that's going to be a key point in developing, ensuring the efficiency of this algorithm. And so one consequence of that is this part here. If I exclude the first term, G1 transpose, and look at the rest, the first row and column of everything that I've boxed here must be entirely 0. So what that means is the first, so a consequence of that is the first column of A has to equal the first column of G1 transpose. Okay. Because nothing else here can possibly make any contribution to the first column of A due to being entirely 0 there. Now I'm going to write this in terms of, here I've written that out in words. Now I'm going to write that out as in terms of a matrix multiplication. Because what is the first column of A? First column of A is A times E1. Now, I mentioned this a couple times, just to make sure it really sinks in, because it has to be like second nature. Just like you know that the derivative of x squared is 2x. E1 is the first column of identity, a 1 followed by all zeros. So this is the first column of A. And then the first column of G1, G1 transpose, I also multiply by E1. Now, this, actually, I hadn't even planned this, but works out nicely. One of the nice things about when you have an outer product is that when you take a matrix like this as an outer product and multiply it by a vector, like I've done here, that is an inner product. In other words, it's just a number. So, what is that number? It's the first element of G1. So I still have this vector here. And then that dot product is just G11. And the reason for that is, what is a dot? It's a dot product. What is a dot product? I'm taking elements of this, multiplying corresponding elements, and then adding them all up. But everything here is 0. Except for the first one. That's why it's only going to take the first element. Okay. So, now, I can go ahead and here I have a vector equation. So now I can just write out this equation element by element. So first column of A, A11, A21, down to AN1, equals, all right, G11 squared, G21, G11, and so on, down to GN1, G11. So now, and this had been worked out last time in a different way, but now we see, okay, here's how we get all the elements of G1. We solve each of these equations. And that leads to G11 being a square root of A11. And all others, GI1 is AI1 over G11 for everything else. Okay. So now we have G1. Any questions so far? Once we have G1, we need to move on to G2. So we'd like to proceed in a similar fashion. And the way we can do that is I'm going to call this A1 to be the original A. And I'm going to take this term, G1, G1 transpose, move it to the other side. And I'm going to move these to the other side too. A lot of people throw trash in the recycle bin. So let's get subtracted off. Okay. So that is going to be all the other outer products. Okay. Now, what I already said about this is first row and column are entirely 0. So we can ignore them. So that's going to be true of the left side also. So, so then what we can do is, so this has a structure like this. Zeros across the top, zeros down the left. And in here, we still have stuff. So, and of course that's going to be true on both sides. So now what I can do is forget about the first row and column, since there's 0 anyway, and just focus on this. So the idea is I can use that first column of this leftover part. And I can use that to get G2 in the same way I just showed with G1. So we keep whittling down the matrix. So after I work on this, I'll subtract, I guess, the non-zero part of G2 transpose off of that, and just keep going from left to right until I'm down to a 1-by-1 matrix, and then I'm finished. Okay. So a lot of matrix algorithms proceed that way, where you're just cutting down the size of a problem one step at a time. So starting with my original n by n matrix, now this is n minus 1 by n minus 1, and so forth, until it's all finished. So in other words, G22 would be the square root of if I take this matrix, A1, and look at the 2-2 entry, which plays the same role as a 1-1 entry did in the original matrix, because it is a 1-1 entry of that spot, of its block. And then all other entries of G2 would be the corresponding entry of A1 divided by G22. This is for I equal 3 up to n. Now, I've included this superscript here so you can see for yourself, okay, that's not the original A. It's an updated A, just to avoid confusion. However, here's another thing, is the distinction between how you're writing these things out mathematically or when you're implementing them in code. Because in code, you might be perfectly fine with overwriting something. That's actually what we would do, because when you're implementing a Cholesky factorization like in MATLAB, you're not going to store A, then A1, and then later A2, A3, and so forth. You don't want to store all those. That's completely wasteful. You just keep overwriting A, because you already have A probably saved somewhere, or it got passed to your function as a parameter. It's not going to get lost. But within your function that implements Cholesky, you can keep overwriting it and saving storage. So these are sort of things that no one cares about when you're working problems on a paper. It just doesn't enter your mind at all. But in code, it's actually crucial. Okay. So from what I've written here, I can show you what the actual algorithm would look like in like pseudocode, something that could be easily translated into MATLAB, for instance. All right. So I'm going to write that over here. Now, from what I've already done, you can see that we're proceeding from left to right, between G1, G2, and so forth, all the way to Gn. So I'm going to use J as my column index. So inside this loop, the goal is to compute Gj. So the idea is you go ahead and compute the current G, so starting with G1, and then you update A to set up a computation of the next G. So for computing Gj, I'll have, all right. So Gjj is the square root of KJJ, where we assume that the matrix A either is the initial matrix for G1 or it's the updated matrix after subtracting off outer products. I haven't shown you how we do that yet. We're going to assume that's the case, and then we'll make it happen. So we take a square root up front, and then all other entries in GJ, all non-zero entries, so j plus 1 all the way to n. So this, I'm using like a MATLAB-like syntax here. So this is range of numbers starting at j plus 1, j plus 2, and so forth, all the way to n, just for compactness. And that would be equal to A, rows j plus 1 to n, still column j, divided by g, jj. So what these statements do is compute the non-zero part of gj. So you're filling in part of your Cholesky factor. Okay, just as I showed over there. Okay. Next thing to do you want to subtract off GJ transpose to set up A for the next iteration. Okay, now we have to keep in mind that this matrix has certain rows and columns that are all zero, so we want to skip over those. Because keep in mind, GJ transpose, element IK, well, that's the outer product. I wrote down the formula for that last time, so I'll repeat it here. So it's going to be the ith entry of this vector, which is Gij, times the kth entry of this vector, which is going to be Gkj. So, in other words, this is what I have to subtract off. So, I need a loop, two nested loops actually, for I equals, and I'll fill this in a moment. So I'm going to loop over rows, and I'm going to loop over columns. And I'm going to perform this update. AIK is equal to itself minus this, the IK entry of this, which I've written here. Gij, Gkj. That's the whole algorithm, except I have to fill in what goes here. So we figure out each column of a Cholesky factor, the jth column, subtract off the corresponding outer product from A to set up the next iteration. Okay. Now, there are three ways I can fill in these loops. There's the incredibly naive and inefficient way, there's the less inefficient way, and then there's the actual efficient way. I'm going to cover all three. So, a stupid way to do this is think, oh, these are n by n matrices. So I'll just go from 1 to n. Might not want to write that, or if you did, hopefully in pencil. This is correct mathematically and incredibly wasteful because, as I mentioned earlier, certain rows and columns of this outer product, GJ transpose, are zero. We're subtracting a zillion zeros from A. So let's not do that. Because the first j minus 1 entries of Gj are zero. So what we can do is start at so we can start at row j and also start at column j. So that's an improvement. So this skips over for rows, the elements of Gj, therefore for rows and columns of this outer product that we know are 0. So that's a start. Now, it turns out that we can do better because if I go back to what I showed you here, like, for example, if j equals 1, that means we're still subtracting off everything. We're subtracting off G1, G1 transpose from the entire original matrix to get this. And what do we see here? We know the first row and column are going to be 0. Okay, actually, I think so at least I can avoid having, dealing with, so I have to make sure that I have this correct. Yeah. So all I'm doing here is I'm performing a subtraction that I know is going to get me 0. So why do it if you know what the result's going to be? Because you can just put zeros there if it's more efficient. So that means I need to tweak my loop boundaries a little bit, and I'm going to cheat here and make sure that I'm not giving the wrong algorithm in the end. Okay. All right, yep, everything's good. Because, like I said, I'm winging it. Okay. Oh, I'm so sorry. Especially to you, Kristen, because you're watching us here. I crossed into the glare zone.
I was
Okay.
going to tell you after you finished.
Okay, so.
It's okay, I'm sending her my notes.
All right, and this says loop over columns. Okay. All right, so to fix that, I just need to change these from j to j plus 1. All right, so that trims out a lot. But it turns out we can do better still. So if you were to look at the algorithm that I have in my book, and I think might also be in the notes, these are not the loop boundaries, or at least it is for one of them. The outer loop does go from j plus 1 to n. But here I can do better. Instead of stopping at n, going all the way to the end of matrix, I actually stop at I. And that's going to look like completely incorrect. Like, why would you do that? You're only updating part of A. So why is it still okay? Here's why it is. So yeah, this is my final iteration. You can write this down. So this ensures that K is less than or equal to I, and when the column index is less than or equal to the row index, what that means is you are not updating all of A, you're only updating the lower triangle of A. So the main diagonal you are updating, and everything that lies below it. Now, does anyone tell me, see how well you've been paying attention, something like this would definitely not be okay in a Gaussian elimination setting. Why is it okay here to only touch the lower triangle? How come we're allowed to completely ignore the upper triangle of A? Yes, specifically because A is a symmetric matrix. The upper triangle is the same. So, and in fact, because what's happening here is the goal is not to wipe A out. The goal is to compute G. In order to compute G, if you look at these entries here, notice the row index is always greater than or equal to the column index. We are only using the lower triangular entries of A to get the entries of G, which is also lower triangular. So a lot of times when you're implementing algorithms, you end up doing more than is actually needed, just to try to have results look a certain way. Like if you're implementing Gaussian elimination, you want to see A reduced to actual upper triangular form. You don't have to do that. You just need those correct entries in the lower triangle. Don't waste time zeroing out the other ones. That's a wasted operation. So, so we're only touching half the matrix, and this seems like a small thing, but it's actually the most important thing in terms of justifying why we do this instead of Gaussian elimination. So the result of all this is the cost of this algorithm is roughly 1/3 n cubed floating point operations, compared to Gaussian elimination, which is how many? 2/3. So by touching only about half the matrix, we save ourselves half the operations. So that's why if you're solving a symmetric positive definite system, yes, you could use Gaussian elimination, but Cholesky will be twice as fast. So that's why it's normally used in this situation. Also, so any questions about how this algorithm came to be? So this is how numerical linear algebra works, is that every operation matters, and we pay attention to the structure of the matrices we're working with to try to minimize how many operations we perform to get the most efficient algorithm possible in terms of number of arithmetic operations, also in terms of storage. So, because in real applications, you're dealing with matrices of millions or maybe even billions of rows. Yes, I'm not exaggerating, like especially with supercomputers at the national labs. So both elements matter, how fast and how much space. Okay. Oh, I haven't chewed up too much time, so that's good. Okay. Now, a couple other points I want to make about symmetric positive definite systems before moving on to the other topic I have planned for today and we'll hopefully get through. So I have to go back to a certain subtopic of the LU decomposition. In terms of existence. The LU decomposition is unique, and it's a rather non-interesting proof to show that. So I'm not really going to talk about that, but we do want to talk about existence. Not every matrix, so if A is invertible, this factorization, PA equals LU, where P is a permutation matrix that rearranges the rows of A. This is for row interchanges. This factorization can always be achieved. If there's some need to interchange rows to avoid a division by zero during Gaussian elimination, you go ahead and, if it's a matrix invertible, you can always find a row to interchange with to make that happen. But just plain old A equals LU, not necessarily possible. So for instance, I have an invertible matrix where the 1-1 entry is 0. I can't factor that as A equals LU. So I can here's a condition for A equals LU to exist. I need to introduce some terminology for that. So in my matrix A, suppose I take the first K rows and columns. So the upper left block, that's K by K. So I'll call that AK, which is in MATLAB syntax, you specify a range of rows and columns, 1 to K, 1 to K. And this is called a leading principle. Oh God, just saying people use the wrong one. Principal, this is principle, and I just screwed it up. At least I caught myself. So principal for mortgages and whoever rules a high school. But so, okay. Yeah, principle for morals, I guess, and pretty much nothing else. Okay. So leading principal submatrix of A. All right. But what I really care about is M sub K, which I define to be the determinant of AK. Leading principal minor of A. Sometimes we just call it a minor, and the leading principal part is understood. Because I guess you can have trailing submatrices for minors, but no one ever talks about them. Okay, so using that, this jargon here, A equals LU is possible if and only if all of the minors are non-zero. So if any of those minors are 0, pivoting is required. So for instance, suppose a 1-1 entry is 0. That means that M1 is 0. And you'd have to do a row interchange. Let's see. Another example, more interesting, would be this. So here's a matrix where the 1-1 entry is non-zero. But let's suppose I perform Gaussian elimination, and I eliminate entries in the first column. So I double the second row and subtract it. Sorry, double the first row and subtract it from the second, and I'll get 0, 0, minus 20, and then triple and subtract, so 0, minus 5, minus 6, minus 11, minus 8. So that's a result of eliminating entries in the first column, and now because of that 0 there, I must pivot. I have to do a row interchange for Gaussian elimination to continue, because the determinant of that upper left 2 by 2 block, I contrived that to be 0. Okay. So if any of these blocks, the 1, 1, 2, 2, 3, 3, and so forth, have a 0 determinant, you must pivot. Now, to tie that back to Cholesky and symmetric positive definite, I can give another characterization of symmetric positive definite. A is symmetric positive definite if and only if it is symmetric and all the minors are strictly positive. So what that means is the minors of a symmetric positive definite matrix can never be 0. So what that means is you never need to pivot. You'll never have a situation like if you're doing Gaussian elimination or Cholesky, where some division by 0 is going to come up. It might still be a good idea to pivot to contain round-off error, but it will never be required. So that's one nice thing about symmetric positive definite case. Another thing to mention about actually symmetric matrices in general, whether it's positive definite or not, there's another factorization that's related to Cholesky. This factorization, LDL transpose, so it's just referred to as the LDLT factorization. Sounds like a pesticide or something. Where L is unit lower triangular. In fact, this L is literally the L from the LU decomposition. It's the same matrix. And then D is a diagonal matrix. So you can think of this DL transpose as being the U in the LU decomposition, because in fact it actually is. It's just that if A is symmetric and you factor out the diagonal entries, then what we have here, the matrices left on left and right, happen to be transposes of each other. And that's something you can prove in a case where A is symmetric. So in fact, if A is SPD, we can relate these to Cholesky. G is equal to L times the square root of D, where you're just taking the square roots of the diagonal entries, which should all be positive. So for that reason, the LDLT factorization is also known as square root free Cholesky. Because computing the LDLT factorization, I won't go into it here, but it's in the notes or the book. It's similar to Gaussian elimination. So it doesn't require any square roots, but it exploits the fact that A is symmetric to again save operations. So it again takes 1/3 n cubed operations. So this can be used for a general symmetric matrix. It doesn't have to be positive definite. But if it's not symmetric positive definite, like if it's symmetric indefinite, like eigenvalues both positive and negative, it may be necessary to pivot after all. But if you're going to pivot, you don't want to just swap rows, because that would destroy symmetry. So if you're going to pivot, you should pivot in a symmetric manner. That means swapping rows and columns. So if you decide to swap rows 1 and 2, then swap columns 1 and 2 also. So if you do that, then you can preserve symmetry. So I didn't want to spend much time on this factorization, but I just want to make you aware that this is another factorization that's out there for symmetric and SPD systems. In MATLAB, wait, make sure this is still going. Okay. So there is a function, CHOL, Chol, for Cholesky. But one thing I want to make you aware of, it's a little different than what I've written here. R is upper triangular, so it's R transpose R instead of GG transpose. So in other words, to equate to my notation, R is G transpose. So it's still lower triangular times upper, and the factors are transposed of each other. It's just a different notational convention. I just like using the GG transpose. And it depends on what book you're looking at, but different conventions are used. So that's one thing to be aware of. And there is a function for LDLT also. That's what it's called, LDLT. Or actually, I should make sure of that. it might be named something different. Oh, yep, I messed up. It's just LDL. But people tend to call it LDLT. Okay, so questions about symmetric or SPD systems? Okay. So later when we get to iterative methods, there'll be some iterative methods that are specifically for symmetric or symmetric cause definite systems, such as the famous conjugate gradient method, which will be pretty painful to cover. Okay, so during the rest of the time, we'll talk about instead of algorithms for solving AX equals B, how we study the accuracy of such algorithms, and how do we get a handle on the error that can occur from these methods, because you're doing floating point arithmetic. But to even be able to talk about that, I first need to talk about how we describe like the magnitude of a vector or matrix. Okay. Oh, sorry. Okay. So better mark out the glare zone. Okay. Actually, that wasn't entirely accurate.
A little more. Okay. And a little that one.
Yeah.
There you go. Yeah. That's better. Much better. Almost perfect.
All right. So we're going to talk about norms. So this is in the book. It's in the Appendix B, Section 13. In the notes, better check that. Okay. Okay, norms are covered in. Okay. Sections 2.1 and 2.2. Okay. So when you have this number, we know how to describe the magnitude of a number. That's absolute value. So we want to be able to do the same for a vector or matrix. So we'll talk about vectors first, and then we can matrices are built on top of that. So a vector norm. So a function where we use I've used this notation already some. The double vertical bar is meant to convey a magnitude of a vector or matrix, or also a function, but we won't deal with that in this class. The dot here is just a placeholder. Like this is where I put whatever I'm taking the magnitude of. So it is a function from a vector space like Rn or Cn to the real numbers. So the function like that maps vectors to real numbers is a norm if it meets certain conditions. Probably the most important condition has to be non-negative. Doesn't make sense to have a negative magnitude of anything. Also, the only time that it equals 0 is if the vector you're taking the norm of actually is the 0 vector. So any vector, no matter how small, if it has any non-zero entries in it, must have a strictly positive norm. If you scale a vector by a constant, that scales the norm by the absolute value of that constant. And finally, property you're familiar with from absolute value has to satisfy a triangle inequality. So the norm of a sum of vectors must be less than or equal to sum of the norms. All right. Now, there are many different norms out there, but there's one family of vector norms, which is really the only one we'll deal with. These are called the P norms, also known as the LP norms. And they can all be described using a common formula. So I use a subscript P to indicate which P norm I'm talking about. P will be a number. And all it is you take the absolute value of a components, real or complex, doesn't matter, raise them to the P power, add them all up, raise the sum to the 1 over P power. So these are the P norms. Now, among P norms, there are 3 of interest to us. There is the 1 norm. So that's just the sum of the absolute values. There is the 2 norm, which you may also know as Euclidean length. Often that's talked about as the magnitude of a vector, but this is just one notion of magnitude. So you take the square root of the sum of squares. So we'll certainly make use of these. And then there's one more, the infinity norm. So if you let P go to infinity, the idea is the larger P is, the more the norm tends to emphasize the largest component of the vector. So you take that to its extreme, the infinity norm of a vector is just the absolute value of the largest component. So very easy to compute. But one consequence of how these P norms behave is that also the larger P is, the smaller the norm. So if I just make up a vector, take its 1 norm, 2 norm, infinity norm, or any other norm, the 1 norm would be the largest, and then it'll just keep decreasing from there. So what magnitude a vector has depends on the norm you're using. So that's one thing to be careful about. Like, suppose I'm in the vector space R100, so vectors of length 100. And let's suppose that all the elements are equal to 1. Well, the 1 norm of that vector would be 100. The 2 norm of that vector would be 10, because I'm adding up 100 once and taking the square root. The infinity norm of that vector would be 1. So sometimes those magnitudes can vary greatly if you're in especially in a large dimensional subspace, where the dimension of a subspace, or vector space, plays a role in the norm. One important property that's going to be useful to us now and then, specifically for the 2 norm, is, and you may have seen this in calculus, the Cauchy-Schwarz inequality, which I would take a time to prove, but I don't feel like it today, or just other things I've ever spent time on. And that is the dot product, or absolute value of the dot product of 2 vectors, is less than or equal to the product of the 2 norms of those vectors. Okay. But yeah, in my book, I have a proof of that worked out. The other thing I want to mention about vector norms is they give us a way to define convergence of a sequence of vectors. So limits of vectors in terms of limits of numbers. So we say that the limit as n goes to infinity of a sequence of vectors xn is equal to x if a limit n goes to infinity of xn minus x is 0. So in some norm. Now, even though the norms of vectors can are different for a particular vector, you're not going to have, when you're talking about p norms, you're never going to have a situation where a sequence of vectors converges to a limit in, like, for instance, a 1 norm, and it does not converge in a 2 norm. So all p norms are equivalent in that sense, that if it's, convergence in one norm is equivalent to convergence in another. So you're not going to have that kind of issue. Otherwise, norms would be kind of useless. And this is true if and only if, when we look at each individual component of xn, it's converging to the ith component of x. So convergence of vectors to a limit is exactly the same as convergence of each individual component to a limit. So we have two ways of relating convergence of vectors to convergence of numbers. Okay. Now, from vector norms, we can talk about matrix norms. Now, matrix norms have to have the same properties as vector norms. They can only be 0 for matrix is 0. They must satisfy the triangle inequality. But there's one other property that I'd like to add. This property that if you have the norm of a product of matrices, it needs to be less than or equal to the product of the norms. That is called the submultiplicative property. Not that I'm ever going to quiz you on the name, but so this is very nice for proving various things involving matrix norms. Okay, it's still going. Okay, what? Okay. All right. Now, how do we define a matrix norm? Unfortunately, we can't really define it as easily as we can for a vector norm. We do have matrix P norms, but here's how we define a matrix norm from a vector norm. So we say a matrix norm is induced by a vector norm. So the idea is we define the norm of a matrix A to be the supremum taken over all. Okay, I'm going to assume A is m by n, and x is going to be in Rn, because if you're multiplying A times X, the dimensions have to be compatible. So I take a supremum over all non-zero vectors X of this quantity, a ratio of AX to X. So in other words, it's a maximum extent to which multiplying a vector by A can amplify the vector norm. Now, another way of writing this, which is maybe more convenient, is also the maximum over all vectors of unit length. So basically, the unit sphere with respect to this norm of just plain old AX, because we don't need a denominator because it's 1. All right. Now, one subtle point here. Why is it that here I can say maximum of this set when I cannot here? I have to settle for saying supremum. Don't suppose anyone knows the answer.
Because of the boundary?
Well, it's kind of related to that. This set of all vectors with magnitude 1 is a compact set, closed and bounded. That is not, because it's the whole space with one point taken out. And my apologies to those who were recently traumatized by real analysis.
That was a couple years ago, but I'm still traumatized.
Okay.
Something I'll never forget.
Yeah. So there's no getting away from all that stuff entirely, but mostly. Okay. Now, this definition is kind of a pain to work with. So, but the idea is for certain norms, like the counterparts to the norms over there, I can write down formulas for them, and they would be proved using this definition, which I won't take the time to do here because, but here are the norms that correspond to the vector norms over there. So the matrix 1 norm, what we do is we take a maximum over all columns of a sum of the absolute value of entries in that column. So informally, it's the maximum column sum. So you go for each column, sum up the absolute values of all the entries in that column. Whichever column sum is the largest, that's the 1 norm. So something that would be proved using either of these definitions. Let's see, actually, I believe in like the notes in the book, may have worked out one of them. Okay, like in the book, I've worked out, the 1 norm. The infinity norm would be similar. The infinity norm is the maximum row sum. So in fact, you can say that the infinity norm of A is the same as the 1 norm of the transpose. Okay. Alrighty. And then, unfortunately, the 2 norm of a matrix, let's see, I won't take the time to work through the calculus on this. Okay. For the matrix 2 norm, there is no formula like these to describe a matrix 2 norm. So in fact, if you're computing norms in MATLAB, I'd actually encourage you to use one of these, or there's one of our norm we'll introduce later, but not the 2 norm, simply because it actually would be more expensive to compute, possibly a lot more expensive than these. So, because the thing is, okay. I may not do the whole thing, but I can at least give you the idea. Ow, you're dead.
Cold.
Oh, good, I didn't erase the glare zone. Okay. Now, if I define the function g of x to be the 2 norm of ax squared over the 2 norm of x squared. And I'm working with a square because we don't have to write pesky square roots. Because this is the same as x transpose A transpose AX over X transpose X. Because the 2 norm of a vector squared is just the dot product of a vector with itself. So what I can do is I can try to find the maximum of this function using calculus, multivariable calculus. That would involve the quotient rule. So the gradient of g of x, because it's a function of n variables, of the components of x. So this is a function of one variable is a maximum when its derivative is 0. Function of n variables as the maximum or local maximum or minimum, possibly when its gradient is 0. The gradient of g turns out to be, and you can really use a quotient rule for this. So that times the gradient of this, which is 2A transpose AX, minus this, times the gradient of this, which is 2x, all over that squared. Okay. So if I factor out what I can, certainly I can factor out a 2. And I'm going to factor out x transpose x also. Then what's left is A transpose A x minus this quantity, which is a number, times x. And I want this to be equal to the 0 vector for a local max or local min. So it turns out that what we have here is if I want A transpose A x to be equal to a multiple of x, that means that x is an eigenvector of A, and this quantity is the eigenvalue. So this is an eigenvalue problem. So what that means is the 2 norm of A is the square root of the largest eigenvalue of this matrix here, A transpose A. Not an easy thing to compute, unfortunately, but more useful in theoretical settings. When I talk about the singular value decomposition later, I could tell you that, or this would have meaning then, that this is also equal to the largest singular value of A. Okay, so this is a matrix 2 norm. Now, MATLAB has a norm function. So if you call the norm function, it will compute whatever norm of whatever matrix or vector you give it. Its default is the 2 norm. So that's one thing to be aware of. And there's one other matrix norm that is easier to compute. It's called a Frobenius norm. And this is different in that it is not induced by any vector norm. So the notation is we use a subscript f for Frobenius. And all you do is you take the sum of squares of all the entries in the matrix and take the square root. So in other words, it'd be like if you took the matrix and you reshaped it into a vector, a big long vector, and took its vector 2 norm, that would be the same as the Frobenius norm. So one thing we can say, actually, is that the 2 norm of a matrix is less than or equal to its Frobenius norm. Because the 2 norm is the square root of the largest eigenvalue of A transpose A. The Frobenius norm is the square root of the sum of all the eigenvalues of A transpose A. Okay, so these norms, 1 norm, 2 norm, infinity norm, Frobenius norm, we're going to see those from time to time. So that we can, because by assigning a magnitude to a vector matrix, that helps us quantify error in approximations. So that's why it's a very crucial concept. And I'm going to use that now for the last topic of the day, just conditioning of AX equals B. And I think I'll just be able to, yeah. So I've covered everything I wanted to today. I think we might wrap a little early, we'll see. No promises. Okay. So this is about the sensitivity of the problem solving AX equals B. Because in general, and those of you who took Math 460 with me saw this for in a more general setting, that when you're trying to solve whatever problem, like AX equals B, sometimes the problem can be badly behaved. And what I mean by that is a small change in the problem data, like changing A or changing B, could result in an unexpectedly large change in the solution. So the problem is particularly sensitive to changes in the data, and that's called ill-conditioned. Ill-conditioned problems are bad because it's not like it affects any method that you would use for solving it. You can't get around it. And there are things you can try to do by incurring greater computational expense, but such problems are extremely challenging. And that's why numerical analysis is such an active research area, because we expend so much effort trying to deal with problems such as ill conditioning. So what I can do is, at least for a problem like A equals B, it's possible to give a concrete measure of how sensitive the problem is. So to define some terms here, suppose we have tried to solve AX equals B using some method, for example, Gaussian elimination and back substitution. And we get an approximate solution, which I'll call X tilde. And I'll just use X to refer to the exact solution. Now, so some terms here. So the error, we'll call E, is just going to be the difference between the two. Exact minus approximation. In 460 terms, absolute error is what this is. Okay. Now, that's what we really want to know. We want to know how much does our computed solution, that includes, for instance, round-off error, etc., how much does it deviate from the exact? But that's not so easy to find out, because if it was, we can get the exact solution. But here's something we can get. The residual, R, we just take our approximate solution and plug it back into the original system. So it's B minus AX. which we want to be 0. And it would be 0 for the exact solution. So let's suppose we've obtained our approximate solution. We go ahead and compute the residual, and we find it's nice and small. So we think, okay, we're done, right? No, you're not. Because a small residual does not necessarily mean a small error. So I'm going to explain why. So what I'm going to do is, I take my error e and multiply by a. So that would be ax minus ax tilde. But x is the exact solution, so ax is b. Which is a residual r. So there is a nice simple relationship between the error and residual. So we can use that and norms to understand that relationship better. Okay. So if I start with that equation, AE is equal to R. Let's see, actually, all right, and A is invertible, so I'm just going to multiply both sides by A inverse. Then I'll take a vector norm. Doesn't really matter which. I'll just use norms that are soon to be compatible with one another. Like if I'm using a vector 1 norm, I'm also using the matrix 1 norm. So I'll take norms of both sides. Okay. Now I'd like to know the relative error. Oh, whoops. I should not have done that yet. I want a relative error, so I'm going to divide both sides by the norm of x. It's a really annoying buzzing.
Those are the bugs outside.
Oh, okay. Well, at least it's warm enough for them to come back. Yeah. Okay. Now, the step I wrote too soon.
Sorry. Why did we divide by the norm of x? We wanted the what?
Relative error.
Relative.
Yeah. Now, the norm of A inverse R is less than or equal to the norm of A inverse times the norm of R. All right, next, I'm going to, on the right side, multiply and divide by the norm of A. Now, let's take a look at what we have in the denominator there, norm of A times norm of x. Well, norm of A times norm of x, using the same properties I used over here, is greater than or equal to the norm of ax, which is just b. All right. But that means if I take 1 over both sides, that means that's 1 over norm of A times norm of x is less than or equal to 1 over norm of b. So that means I'm allowed to replace the denominator by norm of b as long as I use less than or equal to, which I'm using anyway. Okay. So, to conclude, the relative error in x, in my approximation x tilde rather, is less than or equal to this quantity called kappa of A times the relative size of the residual. Because the residual indicates how far B deviates from AX. So the relative residual, you divide by the norm of B. And this quantity, which is a norm of A times the norm of A inverse, is called a condition number of A. So that is how we measure the sensitivity of a problem Ax equals B, prove a condition number. So what that means is, if suppose we change the right-hand side of Ax equals B, we change B, then the, or if we change A, the solution, change of solution can be amplified by up to the condition number. Now that's actually, I haven't actually proved that. But it's something that I can prove separately, but I don't think I'll have, well, I might. But it also shows that the size of a residual can be amplified by as much as the condition number in the error of the solution. So you might have a pretty small residual, but if the condition number of A is quite large, and it can be arbitrarily large. I will say that the condition number is always greater than or equal to 1. So a perfectly conditioned matrix, like identity, its condition number will be 1. But you could have matrices with an extremely large condition number. So you might have a small residual, but have an extremely large error. So that's one thing to be aware of, that don't assume that just because your residual is small, you compute B minus AX, like, oh, it's 10 to the minus 8, it's Miller time. Well, not necessarily. Okay. Now, to see this from a point of view of sensitivity, I should mention, okay, where this came from. Okay, this was actually worked out in the notes, section 3.5 in the book. I'm taking from section 3.4. Okay. Also in the notes, this came from 3.5. There's also a section on sensitivity where I derive this in a different way, 2.11 in the notes, but all of this is in 3.4 in the book. Okay. Now, since I have, sorry about reneging on the early thing, but okay. Well, I just want to give you an idea, because when you're in I just always find it fun when I'm teaching a linear algebra class to bring calculus into it, because I just like mixing different areas of math, and that can be used. That's a good idea to perform what's called perturbation analysis. Like if you're assuming a change in the problem data, what happens to the solution? So you could use Taylor expansion to figure it out. Suppose I have this system, A plus epsilon E times x of epsilon is equal to B plus epsilon little e. Now, this is not error. It's not the same e as over there, so don't do that to me. Okay. Now, if epsilon equals 0, that's just ax equals b. So in other words, x of 0 is just the exact solution x. So the error, or really the perturbation in the solution, is x of epsilon minus x is 0. So if A or B change using these perturbation matrices, capital E here and lowercase e there, what happens to the solution? Well, by Taylor expansion, that would be epsilon x prime of 0 plus additional terms around the order of epsilon squared. So if we can get a handle on x prime of 0, how large might that be? That gives us an indication of sensitivity of the system. So what you can do, sorry.
Is that a D?
Well, no, that's a big O. Order of epsilon squared. Yeah. So what you can do is, all right. I can take the derivative of both sides, or actually the book I just worked out another way, but okay. That's kind of weird, but okay. So if I differentiate both sides with respect to epsilon, then I have a plus epsilon e x prime of epsilon plus e x of epsilon is equal to e. So then what I could do is solve. Well, actually, I can let epsilon equal 0 now. So a x prime of 0 plus ex is equal to e. So now I can solve for x prime. So that's equal to a inverse little e minus big E times x. So what I can do now is try to get a handle on how big that could be. So I could do the same thing as before, where I take norms and work with properties of norms. And it'll work out much like what I just did. So a relative perturbation is x prime of 0, which is roughly x of epsilon minus x, divided by the norm of x. So the relative part. And that is equal to norm of A inverse, little e minus big Ex over norm of x. And using the various properties of norms and multiplying and dividing by norm of A like I did before, that would be less than or equal to condition number from taking these times the norm of E over the norm of B by lumping this in like I did before, plus here I have norm of A inverse norm of A as condition number times norm of capital E, and then this norm of x would cancel with the norm of x down here, and I'm left with norm of A. Okay. So yes, I glossed over the algebra, but that's because I didn't want to keep you late. You're welcome. But if you're not convinced of this, this is where you get practice in working with the properties of norms like I did over here. It works out very similarly. Using a triangle inequality also, that all of this falls out. And what do we have here? Relative change in B this is a relative change in A. So, whatever change occurs in the problem, AX equals B, that amount, the magnitude of that change can be amplified by the condition number of A in a change in the solution. Now, that's potential. You may have a solution X not really change that much at all, but that depends on the A, depends on the B. Now a condition number, unfortunately, is not easy to compute because it involves a norm of A inverse, and I told you guys not to compute A inverse. There are techniques of estimating it. When I talk about the secret value decomposition, I can give you a simple formula for it. That'll be coming up pretty soon. But this marks, with 1 minute to go, the end of Chapter 3 material. Guys, get going on that quiz that I posted in Canvas. That'll be due on Monday. And then the homework problems, if you want to, that's the optional assignment. So if you want to do that, get cracking on those. So we can talk about this next week. But what I'll do starting next week is I'll get into Chapter 4 in the text, which is also Chapter 6 in the notes. Least squares problems. So new to everybody. Okay. Oh, ended exactly on time. Sorry about that.